The turbofan engine is a complex synchronization of several components working together as two parts. A core section that produces power to drive the propulsor section that produces thrust. Thrust is a force created by the acceleration of air. This phenomenon is simply an application of Newton's second law of motion, commonly expressed as force equals mass times acceleration. It is this force that propels the aircraft. To see how this thrust is developed, let's look at the internal workings of Pratt & Whitney's PW4102 turbofan engine. The first component in the engine is the huge 9-foot diameter fan that rotates 2,800 times a minute at takeoff. This giant fan sucks in enough air to vacuum out the air in a 4-bedroom house in less than half a second. As the air races through the massive fan, it's separated into two streams. Only 15% of the air flows into the interior core of the engine. The remaining 85% of the air is ducted along the outside of the core and is forced through an ever-narrowing space, the fan duct, picking up speed along the way. The ratio of this air bypassing the core to the air passing through the core is called the bypass ratio. Because of its huge volume, the bypassed air only needs to accelerate a small amount in order to develop an enormous amount of thrust. Meanwhile, the other 15% of the air has entered the first component in the engine's core, the low-pressure compressor. Here, the air passes through several smaller stages, each consisting of a set of rotating blades in between a set of stationary blades. Each stage compresses the air, forcing its temperature and pressure to rise. After passing through the low-pressure compressor, the air enters the high-pressure compressor, which rotates faster and is responsible for 70% of the total pressure rise. After the air has passed through both compressors, it is 35 times higher in pressure and 1,000 degrees hotter than the outside air. The compressed air is now at the right pressure, but it is moving too fast to be efficiently ignited, so it enters a diffuser, where it slows down while remaining at the optimum temperature and pressure. The air then enters the combustor, where its energy level is greatly increased. This is accomplished by adding fuel through a series of injectors and igniting it, further increasing the temperature of the mixture by 1,600 degrees. The higher the pressure of the air, the more energy will be added during combustion, and the more efficient this process becomes. This is why the compressors were used to increase the air's pressure. Now, the superheated and compressed air mixture is ready for the next phase. Blasting through the high-pressure turbine, the high-energy air spins the blades at over 10,000 revolutions per minute. These blades are connected to a shaft that runs through the center of the engine and drives the high-pressure compressor. In fact, the only purpose of the high-pressure turbine is to extract enough energy from the air to turn the high-pressure compressor. Together, these components make up the high spool. Next, the air passes through the larger low-pressure turbine. This turbine has two purposes. First, it extracts enough energy from the air to power the low-pressure compressor at the front of the engine core. These two components are connected via a second shaft, which actually passes through the center of the high spool. However, the second and more important job of the low-pressure turbine is to turn the large titanium fan blades up front. The fan is connected to the same shaft as the low-pressure compressor and low-pressure turbine. Together, these three components make up the low spool. Finally, the combusted air races out through the exhaust nozzle at the back of the engine to be accelerated one last time. The speed at which this gas exits the nozzle is called jet velocity. This exhaust stream produces only 20% of the engine's total thrust. The remaining 80% is produced by the large volume of accelerated bypass air exiting the fan duct.